All right, so in this tutorial, we're going to look at a phenomenon called wave interference. Very important in nature. It happens everywhere in nature. We're going to look at some visuals, do some problems, and then this is coupled with the demonstrations we did in class before this tutorial and after this tutorial. So let's jump right into it. So waves, unlike particles, do not collide. All right, so big picture here is very often when you have sources of waves, there's more than one source, or there's multiple waves, multiple frequencies, and they overlap. And so when they overlap, we have to understand how the wave behaves when they overlap. So that's the context behind this statement here. When waves overlap, they don't collide and conserve momentum, bounce off each other. No, no, no. When they encounter one another, they interfere. Okay, what does that mean? Okay, is that for a short period of time, whenever they're overlapping, the wave's amplitude can be greatly increased or decreased. And so an interference effect is essentially changing how high the amplitude of the wave is or how low it is. In other words, they can basically build up to bigger amplitudes, or they can reduce to smaller or no amplitudes. All right, so almost any wave phenomenon we're talking about involves interference. It's very, very important. So the two main types of interference are constructive and destructive. The names kind of tell you what happens. In a constructive interference, the waves meet and get bigger. It can be as much as twice the original amplitude or some fraction therein. Right? So in the diagram you see here, you have two waves, the red and the blue wave, or I guess in your paper it would be one moving to the left and one moving to the right. At a certain time, they will completely overlap. And when they overlap at time one, you don't see two separate waves, you see the superposition of the two. Superposition is a fancy term for what the waveform looks like based on the respective amplitudes for each part of the wave. In this one, we see that the amplitudes add to give us twice the original amplitude. And then afterwards, this is at time two, the waves continue on as if they never interacted with one another. So notice that the wave that we call, I'm going to call this one A and this one B. This is B here, and this is A here. So they didn't bounce off one another. They just passed right through each other, but for a moment, they were basically acting as one unit. If we have wave trains, if we look at the series of wave trains, we have wave A, we have wave B, and note that they are in phase with one another. In other words, when one is a crest, the other is a crest. When one's a trough, the other is a trough. So the key thing about constructive interference is the waves must meet in phase. Another way to look at that is that they are n wavelengths apart. Okay, where n is an integer. This can be 0, 1, 2, 3, etc. So this wave and this wave are in sync. They're one wavelength apart. Or if I compare A to B, they're always in the same, every particle is in the same position at the same time. So if we look at the superposition right here, A plus B, we get the same waveform in terms of wavelength and frequency, but notice it has twice the amplitude. That's the superposition. So if we were playing a sound that was both wave A and B, what you would hear is not two separate sounds, but one sound that is the same frequency as both, but twice the amplitude. Okay, destructive interference is essentially the opposite. Okay, it's when two or more waves meet that are completely out of phase. So going back to our diagram, we have wave A, we have wave B. They are headed towards each other. One is a crest, one is a trough. In other words, they're out of phase. And when they meet right here, there's no wave anymore. They completely cancel out because they had the same amplitudes. If this was a positive 3, this is a negative 3. All right? If they had different amplitudes, then there would be some cancellation, but not complete cancellation. And then afterwards, the waves reappeared. B is to the left, A is to the right. And so if we have a series of waves, again, we can see that when this is a crest, that's a trough. When that's a trough, this is a crest. They're completely out of phase, and so the superposition is nothing more than a flat line. At all times, they are continually canceling out. And so we can do that with two sounds that are completely out of phase. They will cancel out exactly, and I can show that with Audacity if I haven't shown it already. So what does it mean to be out of phase in terms of length? They are odd half wavelengths apart. We'll see the importance of that in the next page. Okay, so n again is an integer, so it's either 1/2, 3/2, 5/2, etc. All right, so a skill that we have to be able to do when trying to do superpositions of waves, all right, is just draw a waveform. So for example, suppose I have a wave that looks like that. It's a very long wavelength. And then I have another wave that has a very short wavelength. And they're played at the same time. And they overlap and interfere. What will the waveforms look like? Well, this is the picture of the superposition. Okay, again. And so what you would hear or see is not two individual waves, but the superposition. And all that's being done is the amplitude of this is being added to the amplitude of that. And the amplitude here is being added to the amplitude right there. And for every single point, we get this waveform. And so this last picture just shows the superposition superimposed on both. So how do we do that for problems here? So let's say I have simpler waves. I have wave A, which is a big square wave with just one period. And then I have wave B, which is a multiple periods. And I want to know what the superposition looks like. Essentially what you do is you take the amplitudes at every given spot and you add them to the other one and put it all together. Okay, so the key is just choosing them at the right time. So let's take from here to here before they meet. I know that. So this amplitude of this one, let's call this 1. The amplitude of each one of these is also 1. So I have for this region right here, 1 for all the way across to here, plus 0. So for that first time, and I am going to start right here, my wave is going to look just like it does for part A. So that's an amplitude of 1. Okay, now I'm going to go to a different color. Now I'm going to look at this section right here when they overlap. So in this region here, A has an amplitude of 1, B has an amplitude of 1. So 1 plus 1 gives me 2. So in this little gap here, I know my amplitude is going to be twice as high. Okay, now I'm going to look at the next section right here, 1 plus negative 1. All right, so again, these should be perfectly lined. 1 plus negative 1 gives me 0. So now it's going to drop down. All right, now I'm going to look at the next zone. All right, so the next zone is this one plus this one. Negative 1 plus positive 1 is still 0. Then I look at this zone, negative 1 plus negative 1 gives me negative 2. So I'm going to drop down. Again, this is misaligned on the smart board. Okay, so there's negative 2. And then for this zone, which is negative 1 plus 0, gives me negative 1. Again, I apologize for it. So there is our superposition of waves. Because we have a slightly more complex waveform. And so if this was a sound, two sounds overlapping, okay, it would be a little bit more interesting than a monotone. We'll do more practice with this on the homework, but that's the idea.